Hello, AP students, and you're looking at our last podcast, podcast 4 of Kinetics. These are the list of vocabulary and the learning goals for the big idea number 4. Okay, so in this video, you should know all these different vocabulary terms here. Okay, you should know that a reaction mechanism is a multi-step reaction consisting of a series of elementary steps that add up to the overall reaction. Okay, you should know that there is a rate determining step, the slow step, and you should know that intermediates are formed, which are then used up in the next step, but play an important role in these reaction series. Okay, and so just understand the basic idea that reactions proceed by a series of elementary steps. Okay, and make sure that you can determine if a reaction mechanism is acceptable based on the requirements that the series of steps add up to the overall balanced equation, and that the slow step agrees with the experimentally determined rate law. Okay. Also, you should know that the collision theory is the idea behind kinetics. Okay, not all collisions are successful, but the magnitude and temperature dependence of a collision is contained in the rate constant, so only temperature can change K. Okay, not all collisions are successful, as I said, but in order to be successful, they have to overcome the activation energy barrier, okay, collide with sufficient energy to break bonds, and the orientations of the collision must be appropriate for the bonds to break and new bonds to form. Okay, so you want to be able to explain the difference between collisions that convert reactants to products and those that don't, based on the idea of activation energy, orientation, and temperature. Okay, and so lastly, you want to understand the idea of a catalyst and how a catalyst speeds up a chemical reaction by lowering the activation energy of the elementary step. And remember, the rate law is drawn or written from the elementary step as well as provided experimentally. Okay, so the bottom idea is reaction rates may be increased by the presence of a catalyst. And catalysts come in many forms. There's acid-base catalyst, surface catalyst, enzyme catalyst, and so on. But just connect the idea with the kinetics concept that catalysts speed up the reaction by lowering the activation energy when creating a new reaction mechanism. Reaction mechanisms are the play-by-play of the molecules and atoms interacting to go from reactant to product. We call this a series of elementary steps. So we try to determine what's happening within the reaction as it eventually goes from reactant to product. So we have transition states forming, and we have intermediates forming. And an intermediate is a substance that forms in one step and then in the next step gets used up, so you don't see it in the product. Okay, so let's look at a mechanism of a reaction in the next slide. Okay, a little technical glitch there. All right, so we have NO2 reacting with CO to produce NO and CO2. Okay, so in the first step, it looks like we've got NO2 reacting with NO2. Okay, and then it's forming NO3 and CO. No, NO, sorry. Okay, now this NO3 is being used up in the second step with CO and forming NO2 and CO2. I think this should just be NO. Okay, but anyway, you can see the idea that this is a series of steps showing individual collisions to go from the reactants to the products. Okay, now the steps are categorized based on how many substances are colliding. So if one molecule is only involved, we call that a unimolecular elementary step, okay? And it's basically rate law of first order. If we have a collision of two substances, then we have a bimolecular elementary step, and it's a rate law of second order. If we have termolecular, that's a reaction involving three or more substances, and it is a rate law of third order. And this rarely happens when you can get three substances colliding in the right orientation with the right amount of energy to break the bonds needed to recollide. It's not very common, so you don't see those very often. Okay, now in your series of steps, one of the steps will be slower than the others, okay, and this is called the rate determining step. Okay, and the rate determining step, of course, determines the rate law because that's the step that determines how quickly the reaction can go, which is the purpose of the rate law. It also gives the molecularity of the overall reaction. So you technically can write a rate law from the rate determining step, the slow step. Okay, now in order for a reaction mechanism to be plausible, meaning it's possible that that is the mechanism for that reaction, the elementary steps must add together to give the overall balanced equation, and the slow step must agree with the rate law that's been given, or the experimentally determined rate law. Okay, so these are the requirements for a reaction mechanism to be plausible. Okay, so here's an example of dinitrogen pentaoxide decomposition, so you can see it playing out the series of steps. Okay.
The decomposition of dinitrogen pentoxide is believed to follow a three-step mechanism. Step 1 is a fast equilibrium. Step 2 is the slow rate-limiting step. Step 3 is another fast step.
Okay, so now let's look at the next slide. Okay. Okay, so here is that same reaction now that you just saw in the video, drawn as a reaction mechanism. Okay, and so you can see the overall reaction at the top and then the individual three steps below. Now, we see that we really work with two dinitrogen pentaoxides, but they're only showing one here. So to prove that that's there, we just set up a parameter like this, where you put the two on the outside. But the individual atoms are or molecules are what we're trying to look at. Okay, now notice the intermediates, NO3, intermediate, okay? So that gets canceled out as we're adding these together. Think of adding algebra equations together, like terms on each side get canceled, okay? So we're canceling out the NO3. That's an intermediate. It's not going to appear in the overall reaction, okay? We're going to continue canceling like terms. I see NO2 on both sides, okay? So we're going to cancel those. And I also see NO, so we're going to cancel those. All right, and so now what's left should add together to give you the overall reaction at the top. So if we multiplied this through, we'd have 2 N2O5s and 2 NO2s. We'd have 1 oxygen and another 2 NO2s, which would give us 4 NO2s, which then does show that overall reaction has been formed. And so this is a plausible reaction mechanism for that reaction. All right, here's a practice problem to help you understand writing reaction mechanisms or rate laws from reaction mechanisms. And so this is question 62 from your textbook. Okay, and so we are given these two steps in this reaction, and it's a reaction of nitrogen dioxide with carbon monoxide. It's forming nitric oxide and carbon dioxide. Okay, and so what will be the rate law? Well, the rate law gets written from the slow step. This is the rate determining step. So this is the step that determines how fast the reaction will go. Okay, and then let's get the overall balanced equation to show that this is a plausible rate law. Okay, so here's the same question written out. Okay, let me shrink this down a little bit so you can see it. Okay, and so our goal is to write the rate law. So the rate equals K. All right, and now here's our reactants, and the rate law is written from the reactants. This is bimolecular, and so we have NO2 twice. So that's the rate law, and so it's second order. Okay, again pointing out, look, we have an intermediate, a substance formed as a product in one step and then consumed in the next step. Okay, now if you had a catalyst in here, which we don't, we could just add something on here, cat. Okay, that would also appear over here at the end if there was a catalyst. All right, so there is the rate law. Okay, so now let's add these together. And let me use a little darker pen. Let's add these together and get the overall balanced equation. Okay, so I'm going to cancel like terms. Okay. All right, so what's left? So we've got NO2. We've got some CO producing NO and CO2. So there's the overall balanced equation. Okay, and they told us what the reaction was going to be, so we could check to see if we're right. Nitrogen dioxide, carbon monoxide, nitric oxide, and carbon dioxide. Yes, we are correct. Okay. All right, so here's a concept check for you. See if you can write the reaction mechanism. See if you can write the rate law for this reaction mechanism. Okay, and then I'll show you how to do that, just in case you struggled with how to come up with that. All right, here's the answer to your concept check where you are writing a rate law for the mechanism. Okay, so here's the reaction mechanism. Here is the slow step. Okay, so our rate law is going to be rate equals K. Okay, and then here's our two reactants. So we've got D times B. Okay, no coefficients, so first order. If there were coefficients here, then I would use those coefficients in these X and Y positions for first, second, third order, etc. Okay, but now here's the problem with this rate law. D is an intermediate. It's formed here and then it's used here, so it can't appear in the rate law. You can't have intermediates in the rate law. Okay, so how you solve that is you go back up to the fast step that is producing D, and you see what comes from, or what is used to get D, and you set this like an equality. So in essence, A plus B equals D, and so we substitute that in for D because this is what created the intermediate. Okay, so now what's our new rate law? Okay, so rate equals K times A times B times B, which is the same as, kind of getting a little squishy down here, but A times B squared. So that's how they come up with that answer for the rate law. There's the solution. Okay, and then I'll insert a clip to show the answer to that. Solving. All right, the collision model is the basis behind kinetics. Okay, so of course, molecules have to collide to react. That's the bottom line. So what is it about the collision that we have to be thinking about? Well, we have to be thinking about the energy barriers involved in the substances, that barrier that we have to get over. And that's called the activation energy. So you have to have enough activation energy for the molecules to collide and react. The temperatures have to be appropriate so that the molecules are at the correct kinetic energy. And the orientation at which they collide must also be correct in order for it to be a collision that gives a reaction. Okay, so activation energy has to be overcome to produce a chemical reaction, and activation energy can be explained easily with the concept of a match. Okay, so you hold a match in front of you and you breathe some hot air on it. Does the match light? No, because it's not enough activation energy provided. Okay, but now if you slide it along the friction pad on the matchbook, now you've provided enough energy to overcome the barrier of the bonds and the reaction takes place. Okay, so that's part of this collision theory. Okay, so let's show how activation energy and a collision appear, and then we're introducing a profile, an energy profile, with this video clip.
Arrangements as the reaction between nitric oxide and ozone occurs. Initially, the nitric oxide and ozone molecules are separated and are not reacting. The forward reaction proceeding from reactants to products is exothermic by 199.8 kilojoules per mole. Let's see how the energy changes and the molecular changes correspond. As the reactants approach, their energy increases. When the molecules are in a transition state or activated complex, their potential energy is at a maximum. As the transition state is passed and the molecules become more like products, the potential energy decreases. Finally, the molecules reach the energy state characteristic of the products.
Okay, so let's continue to look at energy profiles and the idea of activation energy and energy states. All right. So here's another reaction showing the reactant over here on the left. Okay, 2BRNO. All right, when we provide enough activation energy, okay, that's this potential energy increase. It's like the friction of the match. When we provide enough of that, the molecules begin to break and form new bonds. Now, this substance that forms before the final product is called the transition state or activated complex. So you can see over here on the right in the picture, they're trying to show you the molecular visual of the chemical formula. Okay, and so you see the transition state. Then as the substance begins to look more like the product and becomes more stable, energy is released. And so this is an exothermic reaction because there's less energy in the products than there is in the reactants. Okay, and so I'd like to continue with this idea, so I'm going to insert a clip showing the idea that it's possible to have multiple transition states and intermediates in your energy profiles. Okay, here's an energy profile showing several transition states and their intermediates. Okay, so we have our energy. Units would be kilojoules. Okay, reaction progress, so from reactants to products. Okay, and then here is our Transition states or activated complexes, that's another vocabulary term. Okay, or transition state. Okay, so that's just a molecule, a substance that forms for a split second on its way to this intermediate. Okay, so these are your intermediates. Okay, so you can see two intermediates are formed in these series of steps, all right, till we get to our product. And then this would be activation energy, okay, and this part right here would be the overall energy released. And because products are less energy than reactants, this is exothermic. Okay, if this would have been higher up here, then it would have been endothermic. Okay, and so that's just giving you an idea of where the transition states and intermediates fall along a series of steps. Okay, so quick reminder, concept behind energy theory or collision theory is that collisions have to have enough energy to produce the reaction, okay, so that activation barrier has to be overcome, and they have to be orientated in the right fashion so that they collide to break and produce bonds that are necessary. All right, I want to insert another energy profile after this slide talking about collisions having enough energy and correct orientation, just to get you to review, well, you can't see that very good, get you to review the idea of the profile. Oops, that's worse. Okay, so we'll just take that out of there. Anyway, this is question number 64 from your textbook. Wow. You have to find that right spot. There it is. Woohoo! So draw a rough sketch of the energy profile for each of the following cases. Okay, so notice they give us the overall energy and they give us the activation energy. Okay, so pay attention to the signs. All right, so gotta zoom back out a little bit. All right, so here's A. Delta E is a plus 10. So plus positive means endo. Okay, and then EA, oops, sorry. So a positive 10 means endo, and EA is 25. So that's our activation energy. Okay, so if we were going to draw a profile showing this basic concept, okay, we'd have to have a larger bump, and then we'd have to stop higher than the reactants. Okay, so this is supposed to be roughly 10 kilojoules, and then this is supposed to be 25. Okay, so there's your EA, and there's your delta E. Okay, so that's a profile for the case A. All right, case B now is showing an energy profile where we have a negative 10, so that means the energy's been released. Okay, so negative 10 kilojoules means exothermic. All right, and then we have 50 kilojoules for our activation energy. Okay, so negative 10 exothermic, 50 kilojoules. Okay, so as I draw this one, I'm going to have an even greater bump than I had in the previous one, and then I have to go lower. Okay, so here's my EA of 50, and then here is my difference of 10 kilojoules. Okay, the last one shows a negative EA No, sorry, it's a delta E is negative 50. So again, we're still exothermic, but then we have 50 kilojoules of activation energy. All right, so I'm going to start up a little higher because I'm going to need space down here. So way up and then way down. Okay, maybe not quite this far. Let's draw that one again. I shouldn't go beyond my barriers. Okay, so this is reaction progress. This is our energy. Okay, and then we want a really tall activation energy. I'm going to do it again, I think. Okay, one more time's a charm. Start a little higher, really tall, and then come way down because this has to be, there's my delta E. And then my activation energy. Okay, for my reaction progress. All right, so there was C. So just giving you a little more visual with those energy diagrams to make you feel a little more comfortable with it. Okay, so here's a visual showing the molecular collision of NO and Cl2.
The reaction of gaseous nitric oxide and chlorine to form nitrous chloride occurs spontaneously. In this example, we observe that only collisions that involve the correct orientation of the reactants result in product formation. When the nitric oxide molecules are completely used up to form product, there are still several chlorine molecules remaining. This is an example of a limiting reagent reaction.
Okay, so just another visual showing molecular collisions in correct orientation and a review of limiting reactants. Okay, and finally the concept of catalysts. Catalysts speed up a reaction, but they themselves do not become part of the reaction in the essence that they form a product. Okay, they start out at the beginning of the reaction and they end up at the end of the reaction. Okay, so they don't get consumed themselves. Okay, so how do they do that? Well, they provide a new pathway for the reaction, so they introduce a new reaction mechanism, and that new mechanism has a lower activation energy, which then allows the reaction to move faster because a less barrier has to be overcome. Okay, so here's another energy profile showing how the profile changes when you provide a catalyst. So notice that our activation energy here has just been lowered. Okay, so energy versus reaction progress or reaction coordinate, as you can see, that just means the reaction moving forward. Okay, so it's just a lower bump where the transition state forms. Okay, just a lower activation energy there. Okay, so looking at it in a different visual form, you see that the number of collisions increases at a lower energy. You have more effective collisions with less energy. And so here's a visual showing the catalyst and how it works.
Reactant molecules are mixed in the gas phase. Yet some reactions will not proceed even when reactants collide. A catalyst can be introduced to provide a new pathway for reaction. Catalyst molecules collide with one reactant to form new molecules. In this example, two catalyst molecules react to form two new molecules known as the reaction intermediates. The reaction intermediates will be involved in the reaction, but all of them will be consumed before the reaction ends. The reaction intermediate reacts with the other reactant in the mixture to give the reaction product. The catalyst molecule is regenerated in this step, so the catalyst may go on to form more reaction intermediates. In this way, catalyst molecules are not consumed in the reaction. The final reaction mixture will contain product molecules and catalyst molecules.
Okay, so that was a nice summary of how a catalyst works. Okay, so in this lesson, you should have learned what a reaction mechanism is, okay? You should be able to determine if a reaction mechanism is plausible using the requirements given. You should know that the rate determining step can be used to write the rate law. And you should be able to draw and analyze energy diagrams and explain the purpose of the catalyst and how that catalyst works. Okay, so this is the end of the podcast 4 and the last podcast on kinetics.